Hello and welcome to Tom Talks. Today we're going to be looking at the Magnus effect. Now there's already a bunch of information out there on the Magnus effect, but there are a few things that I really wanted to take a bit of a deeper dive into. So firstly, how does it change with RPM? Is it just a constant linear relationship, or is it a bit more complex than that? I also wanted to delve quickly into the reverse Magnus effect. Exactly how does it happen and why does it happen? And then for a bit of fun at the end, I ran some CFD on a cool little thing called like the Magnawing. So you have the Magnus effect basically aligned with an airfoil to try to decrease separation. So all in all, I think that there's some cool content that I prepared, so it should be a pretty good video. Now first things first, a general recap of Magnus effect. So what we normally expect to see is something like this. We have our airflow coming along a cylinder. It's going to separate at some point around about here. It's going to be symmetrical about this plane. It's going to separate around there on that side, and we're going to have some sort of wake, which is symmetrical over a perfectly time-averaged approach. That's obviously not the case. We'll actually have a von Karman streak vortex, but over a time-averaged approach, it will be symmetrical. Now, Magnus effect occurs when we introduce some rotation to it. Fluid has a viscosity, so at the upper and lower points of this cylinder, we're actually going to change the localized velocity. So in this case on the bottom, we're going to increase the velocity, because we're working with the flow direction, so we're increasing the velocity. At the top, we're actually working against the flow velocity, so we'll decrease the localized flow velocity there. The reason this is happening is because we're dealing with any normal fluid which has viscosity. When anything has viscosity and you rotate with a no slip condition, you're going to naturally affect the outer field. So if you have a jar of honey and you turn it in the middle, or something like paint, you'll still notice that the outer edges are still moving even though you're just touching the central part, and that's because we have viscosity. Now, because we've increase the localized velocity underneath and decrease the localized velocity on top, we flick up our wake like this, and higher velocity, thanks to Bernoulli's equation, we know lower pressure, so we extract a nice low pressure region there underneath this cylinder, and on top we have a higher pressure region, and the green arrow there is our net force, which will be a component of our drag, and in this case our downwards force. Now I like to see the phenomena and then see where it's come from, and more often than not, everything's been done really well in nature because they've had a fair amount of time to iterate it, and we actually see some really cool physics in nature. In this case, you can actually see the Magnus effect used with this. So this is a box mite, and as it jumps, it actually jumps with backspin, so it'll rotate this way, which means it will produce a net lift, which is upwards and backwards for its lift and its drag there, So it can actually jump further, and that's pretty cool. Now, how do we change our coefficient of lift with Magnus effect across different RPM ranges? So I have seen a few approximations of this, which have been largely, I think, derived by experimental data, and this relates a cylinder and its RPM across a range of different Reynolds numbers to a coefficient of lift. Now, I've also seen some equations which are perfectly linear, and I wanted to see really how linear is the relationship. Where do we sit? Because obviously it's not going to be perfectly linear, but how close are we? So I ran some CFD. These are just simple cases. I perform statistical analysis on the user points and use the steady state approach. Ideally you'd use a transient. I just don't have all the computing power in the world. 3.5 million cells, y plus less than 1. Now, here's what I found. I should also mention that I modeled this roughly off a tennis ball, so I used certain parameters that were close to tennis. So obviously the diameter was like a tennis ball, but also my velocities and my RPMs were similar to the top tennis players. Now, the blue line is our negative coefficient of lift, so this time I'm assuming topspin, Our orange line is our coefficient of drag, and I've also put in a lift to drag ratio there. Definitely not linear. So right at the base here, we are quite choppy, and then we have quite a steep gradient, and then towards the end we are very much more linear and a much lower gradient after about that 2,500 RPM mark. This is just a line of best fit through a few points, I should add, that I swept through. Drag is choppy at the start, which is what we'd expect because our coefficient of lift was choppy there, but then it is much more linear. It does taper off slightly a little bit, but is much more linear. And our actual CFD shows exactly what we'd expect. So in this case, coefficient of pressure over the body. Our high pressure region in the front actually remains quite square on, quite horizontal there. It's not moved up or down too much. It will usually move down a tiny bit, but in this case looking like it's very square on. Now as we increase our RPM, as we'd expect, lower coefficient of pressure on the underside and generally higher coefficient of pressure on the top side. We can also look at our loss plot, and these can be quite cool and useful because we're seeing the wake really being kicked up quite a lot with the higher RPM cases. And what you can actually do is begin to draw out effectively where the flow is coming together behind the cylinder. And after you draw these out, you can look at the angle relative to free stream that the flow has effectively curved. So if we take a stagnation point here and draw up a triangle like so, we can see that this angle is significantly smaller than that angle. So effectively we've curved the flow less, you're going to extract less load from it. So obviously with the 5,000 RPM case we've got a much greater coefficient of lift, or in this case a much greater negative coefficient of lift. So how does this match the hand calcs? Well, basically it doesn't. There's a massive delta across the whole range really. Down low there's a big delta, but also as we pass about 2,500 RPM, the linear progression obviously remains linear and we taper off quite a lot, so there's a massive delta towards the end. Now, why is this? Well, obviously hand calculations are never perfect, but I also looked at some experimental data out there on tennis balls. Now, big thing to note is that I assumed smooth surface finish. Surface finish has a massive impact on your results. I assumed smooth surface finish, but generally comparing to real life data, around the 2,500 RPM mark, a lot of people were around this kind of region. Even my CFD looks to be a bit more of an overestimation, but yeah, that's roughly what you'd expect anyway. So the general takeaway is, no, I don't think it's a linear relationship at all. Now, if you're actually going to apply Magnus effect to a real application, there's a lot of other things that you're going to need to consider. So firstly, what's the geometry like? Is it a perfectly round bowl, or after you hit it, is there deformation? Are there creases in the bowl, or is it smooth all the way around? Are there roughness changes throughout the match, for example? The other thing to note is Reynolds number, which is very important, as we'll discuss a little bit later on. And I guess you could look at the transient effects of spin. Now, depends on how fast the spin is increasing and how fast it's decreasing. So I'm talking about acceleration of spin, because that would probably affect your vortex shedding frequency if you looked at this in a transient case, but that would definitely be when you're grasping sort of at the end, and you've got the fundamentals down. But yeah, definitely Magnus effect has been used a lot, especially in sports, and I'm sure that they're doing some very high-end work, experimental and CFD, to gather some trends so you understand the relationships, if it's really worth getting more spin or just going for higher velocity or whatever through whatever application. Now, I mentioned there that Reynolds number is important, and this is especially important if we're looking to encounter the reverse Magnus effect, which, as you guessed, is the reverse of what we'd normally expect. So I've got here a cylinder, and we're spinning around, and we've got our net force downwards and backwards. This is what we normally expect. But let's assume that for this case, we're actually very close to tripping to turbulence. So we're a laminar flow, but we are very close to tripping into a turbulent boundary layer. Let's go ahead and draw out our boundary layers. So our bottom boundary layer is going to look like this. Relative to the bowl on the surface, we aren't actually moving, we're in no slip condition, but we've got quite a lot of velocity relative to the free stream because the bowl is actually rotating with us in this case. You could actually see, there's no reason why you couldn't rotate the bowl so fast that the surface is actually a lot faster, and then it actually slows down into the free stream. But in this case, it doesn't really matter. I've got that. We'll still see the same effect. Now the top surface is going to look like this. So we're working against the onset flow, which is normal, is what we'd expect. And then there's going to be a point where we're actually not moving the flow at all. It's going to be stationary. And in this point, we've got quite a lot of shear. And so I said before, let's assume that we're laminar flow and we're on the very edge of tripping to turbulent. Well, provided that the surface finish is the same throughout and nothing's changing, if there's one side which is going to trip to turbulent, it's obviously going to be the top side because we're shearing the flow. There's more chance for us to begin tumbling and transitioning into that turbulent flow. And now turbulent flow, if we've got turbulent flow, we're going to look like this. So our top side is actually staying attached longer than our bottom side, which is laminar, we're assuming, and the top side is turbulent. Turbulent, slightly thicker boundary layer, a bit more mixing, overcome the adverse pressure gradient a little bit better, and we've got a bit more attachment, higher curvature, and we'll extract a greater load. So in this case, we actually generate a low pressure region on the top of the bowl and a high pressure region on the bottom of the bowl, which means instead of having our force vector going downwards and backwards, we actually have it going upwards and backwards, which is not what we'd normally expect, which is why it's called the reverse Magnus effect. And I didn't actually know about this until a little while ago when I saw it pop up, and that's kind of part of the inspiration for the video. I thought it was quite a cool little effect, something that I didn't think about. Now, what are other applications of Magnus effect? Well, for fun, and because we love CFD, I did a quick case on two different airfoils. Well, actually it's the same airfoil. So on the right here, I've got a NACA 8414, I think, and the same on the left, but I've chopped out the leading edge and I've replaced it with a cylinder which I've set to be rotating. Now I've rotated it in such a way to increase the performance of the airfoil in this case. The primary objective of this study was to see if we could use the Magnus effect on a leading edge application to reduce the separation and thereby be able to run with an element, an airfoil, at a greater angle of attack. Now, in this case, I've actually pushed the airfoils at 8 degrees angle of attack, and I've done that so that we can begin to see a bit of the separation out of that trailing edge, and then we can generally see if there's an improvement with the Magnus effect. So let's have a quick look at the results. This is just a coefficient of pressure, and in general we were very successful. So we had 7% more lift and 19% less drag. So you can clearly see the biggest differentiator there is on the top surface. We've gotten a lower coefficient of pressure pretty much all the way over, and we've got that spike where the actual cylinder is rotating, which is what we'd expect. You can also generally see a higher coefficient of pressure underneath the airfoil, but ever so slightly, especially related to that top side. I've also got a velocity plot here, which is confirming our suspicions that we've decreased separation. Now, let's go into a bit more detail with these. So, I'm going to flick through a few of these. I've got perfectly the same camera point. I'd set up a script for it. So we've got our regular wing and our Magna wing there. Yeah, we'll call it a Magna wing. I've never seen it before, but Magna wing sounds pretty cool, so we'll keep that. Okay, so regular wing, Magna wing. Now, starting at the front of the airfoil, the first thing that we notice is our stagnation point. Now, as you can see, as I flick there, it has looked like it's moved ever so slightly downwards. Now, this is important. Your stagnation point can affect a few things. So I'll draw out a brief sketch. Okay, so the sketch shows two airfoils, one where the stagnation point is very much on the front and one where the stagnation point is much more underneath. Now, the first thing to note when we concentrate on the underside surface is when the stagnation point is lower, you can effectively increase the angle of attack very slightly, or dependent on how much it is lower, of the whole airfoil. Now, this is because we're ramming more air into the bottom side, because our onset flow vector is effectively at a greater delta angle to what our original airfoil actually is. So without changing the geometry as such, we're still actually changing the angle of attack. So that's something that we have to note. In this case, it's very, very minor, but I think that that's why we're seeing that slight increase in coefficient of pressure on the underside of the airfoil. The other thing to note is on the upper side. So when we've decreased our stagnation point height, and especially in this case because we've got the cylinder, we're actually extracting a little bit more curvature out of the flow earlier on. So I'll show you here again. So as you can see, obviously we've got the cylinder working for us. Let's not forget that. It is spinning, so we're increasing our velocity there. But you can see we've got quite a lot of curvature early on with the cylinder compared to the regular. And when you've got more curvature, assuming no separation, you're going to increase your load. Now, I should note another reason why the stagnation point is happier to be lower is because the curvature on the leading edge is constant throughout. We're dealing with a circle, so it's just got a diameter. The curvature is constant, which means the stagnation point is happy to be wherever on that cylinder if you just had a cylinder, because the curvature is the same. If you compare that to a normal wing, the stagnation point doesn't necessarily want to be anywhere but on this leading edge. Obviously we can put it here, but it's much more encouraged to be on that leading edge itself. Now we'll talk about the elephant in the room, which is the separation. Now, as you can see, we have massively decreased our separation, which is the goal of the study. Now, why is this so? Well, the first thing to remember is that let's assume that the cylinder wasn't actually spinning. We've extracted more curvature from the flow earlier on because of the cylinder's roundness. It's got more curvature than the airfoil on that upper side. And because of this, when you extract more curvature, you're typically going to be thickening up your boundary layer a little bit. You're going to be using a bit of energy earlier on, which means that you should separate earlier on. Now, we've actually separated later, which means that we can say that because we've got the Magnus effect working with us, we've actually decreased our losses early on in the airfoil, and that means that we've got a bit more energy towards the tail end to hang on to it. So I've actually got a close-up here of the boundary layer just after the cylinder. This is the regular wing and there's the Magna wing. So you can see there quite a sizable decrease in boundary layer thickness, even though we're just behind the cylinder. So are there actually any applications for this? I don't think so, but I thought it was pretty cool to see anyway. I mean, I'm sure it's banned, but you could use it in STOL, so short takeoff landing competitions, but I'm sure that would be banned, otherwise everyone should be doing it. And also the other thing to note is, if you're doing this to reduce separation and to run at higher angles of attack, and you're not using multi-element wings, then you're probably going to want crazy angles of attack. If you want crazy angles of attack, you should just use a cross-flow fan. So I've seen a paper out there where some people got some insane angles of attack using a cross-flow fan in the middle of the airfoil to help glue the boundary layer down, so you can achieve some outrageous angles of attack without much separation or any separation at all, which I thought was really, really cool. Alright, so that concludes this video. In general, I thought we went over some cool stuff. Definitely not the coolest stuff out there, but I think it was pretty cool. I definitely learned some things, and I hope that you did too. I'll see you in the next video.